Today I am going to talk to you about effective anonymization for query logs, and this is joint work with my colleague Nabil Adam at Rutgers and our students Xiaoyun He and Yuan Hong. So you all know what query logs are. Obviously, I don't need to talk about that. And I guess I'm preaching to the choir when I say that query logs are among the most valuable data that a search engine collects and provides great insight into human behavior. And well, again, you all know, there are several applications of query logs. Query suggestion is just one example. I put in Rutgers and I got a whole bunch of things, over there. So you're responsible for part of this, so you know about it. The question that I want to focus on today is basically the anonymization of query logs, or the question of privacy with respect to query logs. So why do we even care about preserving privacy? That should be somewhat obvious to most of you. Query logs contain lots of personal and sensitive information. Turns out, most of us do search for topics related to us, and that's not a great surprise, right? You will search for, about you, including your own name, or you will search for diseases you may have, personal information, the town you're in, so on and so forth. So when you look at it, when you look at the data within a query log, there is, if you look across all of the queries, there's a lot of data about you that tells, that makes it valuable in some sense, but apart from being valuable, there's also sensitive data. I don't want people to know that I have XYZ disease and so on, and you can link across this and figure this out. However, query logs are also widely used. As I said, they're really valuable, and you want to be able to analyze them and come up with interesting information. It's useful for researchers, it's useful for law enforcement, and so on and so forth. So we want to publish them, perhaps you want to release them. Even if you don't want to release them, you want to keep them, archived in a reasonably safe way, so to speak. So one example, all of you probably know about the AOL Query Log Incident, which happened in 2006, when a couple of the researchers essentially released these logs to academia, and they were, so to speak, anonymized by removing, the direct identification information, but that clearly was not sufficient, right? So I'm sure all of you know, within 3 hours, a New York Times reporter was able to figure out that such and such queries were, referred to a particular person in a particular town, and then effectively get a whole lot of information about that person. So that clearly shows, just doing something about it is not good enough. The bigger problem is adversaries may have a lot of background information. This was just a reporter trying to hunt for things. A typical adversary may have even more information, partial information about you, and can easily tie this in to sort of identify the set of queries you have and come up with more information about you. So that's a gigantic problem. In fact, at AOL, as you might know, the researchers were, effectively fired for this act. So it's a big deal. And as a result of that, even from Google now, we in academia have a lot more trouble to get useful data from you, right, with respect to this. So I'm trying to help myself over here by hopefully coming up with some models that might allow you to share data with me so that I can do some interesting things. But anyway, you may you may pose the question, what the heck? Maybe we don't care about academia. We have all of the brilliant people already in-house. We can do all of the analysis. What if we just keep it all to ourselves? Why do we even care? If I never release it outside of the company, maybe it's safe and secure. Guess what? No, that's not true. One, there is always the fear of hacking and so on. Again, you may say our security systems are really, really good. We can protect our data very well. But then you have the problem of law enforcement. Remember the case of Yahoo in China, where they they had to find out that particular person and report back to the Chinese government, who then pretty much put him in jail for the kinds of things he was searching or publishing. Now, of course, that referred to publishing, but you can apply the same thing over and ahead. And you cannot battle that unless you can say, oh, for technical reasons or for whatever reasons, we only have these versions of the query logs, and you have to show blah, blah, certain requirements for revealing certain kinds of things. So the case I'm trying to make is it's pretty clear that you would like to protect these query logs if you can. It's not just, oh, let me keep it in my safe, secure storage and forget about it. So again, the question is, how can you effectively anonymize query logs? There has been significant work on looking at microdata or relational data anonymization. Roberto has contributed to that as well. But query logs, we may hope to and use some of that work in this context, but query logs are different in many important aspects, and I'll talk more about that in a few minutes. Related work, there's been a lot of interest recently in looking at how to anonymize query logs. Kumar et al. Came up with a method for anonymizing query logs via token-based hashing. You basically take the queries, split it into tokens, hash all of the tokens, and that is what you store. The problem is you still have serious leaks possible even when the order of the tokens is hidden. So they have some solutions, but they themselves point out certain problems even with the solutions over there. Adar suggests that we can simply remove queries that are uniquely identifying, just get rid of that. The problem there is, can you easily figure out, what queries are uniquely identifying? Just infrequency may not be such a great way to figure this out. But even so, the solution proposed there is we can split all of the queries into, multiple secret shares, and only when we have, at least the same query is repeated at least, say, t times, then you could pretty much put all of the shares together to decode and find out what the actual query is. Might work. It's a different question on how you could analyze this and make use of something like this in any case. And again, as I said, infrequency is not always, the only way of identifying, what really is sensitive, so to speak. There's other work by Jones et al., again at CIKM 2007. So as you can see, there's a lot of work in the last year or so which has been looking at this topic. And there they use classifiers to map a sequence of queries into demographic information. And again, they can just show that you can identify candidate users much better using query logs, than just by random chance. So they're really saying there is a problem with this. They don't really give that many solutions on what can you do about it. One thing I want to go back to, since I'm coming more from the relational data perspective, and I'm going to use that perspective in this work, I want to briefly talk about k-anonymity, which is one of the first formal models proposed for protecting relational or microdata, relational data or microdata, so to speak, or microdata release. So Similarity and Sweeney proposed k-anonymity, and the idea behind k-anonymity is very simple. A record is supposed to be k-anonymous if it's indistinguishable from k-1 other records with respect to the quasi-identifiers. And I'll just talk about what quasi-identifiers are in just a minute. But the basic idea is, hey, your sensitive information, it can't be linked to less than k other people, so to speak. Okay? So everything, you basically have an equivalence class of size k, and you can never go back beyond that k. That's the basic idea. It doesn't work perfectly all the times. In fact, there have been better extensions of this, but this was essentially the first. It's widely used, and there are some very easy and intuitive properties that you can understand from this. So again, for example, you may try to identify a man from some released data. All you have is his gender and birth date. Now, supposing you find out that in the release data set there are k people matching that gender and birth date, then the data is k-anonymous. And of course, this is only true if that is true of all people over all combinations of quasi-identifiers, not otherwise. Again, when I'm talking about relational data and k-anonymization, there are three types of attributes. The key attributes, which can basically uniquely identify an individual and obviously are always removed before release, so name, address, and so on, and cell phone too at times. Then you have the quasi-identifiers, which are basically the set of attributes which can potentially reveal who you are. So potentially this can be included along with other information to uniquely identify you. So, and then these attributes you want to somehow change. So you may suppress them, generalize the values, whatever, to give you some form of protection. So an example is the zip code, birth date, and gender together, which actually is sufficient to uniquely identify, about 87% of the US population. So Sweeney came up with this metric. In fact, she was able to find out exactly who the mayor of I think, well, let me see, either Boston or whatever, around the Massachusetts area, she was able to uniquely identify people in that area from, identify their sensitive data in the health records using just these three fields. And this was public information. And of course, sensitive attributes have that sensitive information which you don't want to reveal. So just as a quick example, you may have your hospital patient data, the date of birth, sex, zip code, disease, and you're assuming, hey, I didn't put in any identifying information. I got rid of the key attributes, the SSN, the healthcare ID number, and so on. But as I said, it's not sufficient because when you link this with additional data, by the way, if you know k-anonymity, this is pretty obvious to you. You've seen this before. But for the rest of you, if you link this with other data, such as the voter registration data, guess what? You can actually link by the quasi-identifiers, the date of birth, the sex, and the zip code, or actually just, those three are sufficient to link across both and uniquely identify that individual. And all of a sudden, you know, hey, there's Andre, clearly he matches this record, and he has hepatitis, which clearly is sensitive information you would not typically want to reveal. So that's the problem, and k-anonymity helps with this because you basically transform this data set into a corresponding data set where you can no longer identify that person uniquely. So now if we took Andre's date of birth and the sex and the zip code, yes. Oh, I need to stay over there. All right. Okay, let me stick over here and point using this. Maybe that would work. Yep. All right. So with our k-anonymized data set over here, essentially you would have, if you tried to match using Andre's date of birth, sex, and zip code, now guess what? The sex still stays the same, but they've generalized the zip code. The last two digits have been taken off. And same thing with the date of birth, which has been generalized or bucketized into years. And now you have more than one person who is going to match. And in fact, it will be at least k people who match that. So you have those equivalence classes of size k. So you can no longer know, hey, was it Andre, or it could be k minus 1 other people, hopefully, any of the other people. Now, there are problems with this. There have been better models. I'll talk about that briefly at the end. But I'll just give you one idea for now. One problem that could happen is that all of these people in these equivalence class have the same value for the sensitive attribute. So I have k minus 1 other people. Great. But all of them end up having hepatitis. So then guess what? I really haven't protected myself at all, right? Basically, now I know Andre belongs to this set of k people, but he clearly has hepatitis with probability 1. Protection whatsoever. So that's clearly a problem. That's a limitation of k-anonymity, and there have been better models which actually deal with this as well, including L diversity and so on. But nevertheless, this is actually a decent model. At least it's a starting point, and it's very clear and intuitive, the kind of protection you can get with this. One thing is, once you understand k-anonymity, this is just a model. You need techniques to come up with the right generalization or suppression and so on. So there are many ways to sort of change that original data set, right? You can change this in lots of different ways, and you could get many different data sets which would all satisfy k-anonymity, okay? So which one is good, which one is better, so on and so forth. That depends on the metrics you want to optimize. So again, Roberto, in fact, had worked on this problem where you try and minimize the difference between the original data set and the final data set, right? So essentially, hopefully, that leads to less loss of utility. So the data is still as valuable. It has as much information as before, hopefully. Again, that's not guaranteed because there the metric is just number of differences. Maybe you're just getting rid of, very useful differences, so to speak. So that's not guaranteed, but, at least it gives you, again, a starting point, so to speak. Now let me switch over to query logs. Here is one typical, example of query logs. Now again, if you've seen the AOL data sets at all, this will look very familiar to you. This is the schema that they have, but I would assume this is typical of search engines. Of course, you may be collecting a bit more data and so on, but you're bound to collect, the actual queries, the time at which it was, posed, the URL that was clicked as a result of the query, and the rank of the URL. Was it the first one, the second one, third one, and so on. And again, there may be more data you're collecting. In fact, I would be very interested in finding out what extra, what additional data you're collecting. That's one of the reasons why I'm here. Your feedback would hopefully, further educate me on that. But this is fairly typical. This is the kind of data you would have with a query log. Immediately, you're going to notice, hey, guess what? Query log looks very different from relational data, right? Guess what? The data type is different. You have arbitrary words, unformatted. There's no structure. It's basically unstructured data, and they contain imprecise information. So different queries may mean the same thing. Again, there are different ways people will pose a query. They want the same form of information. People may misspell. That again leads to the same thing. Lots of different things can happen. It's not precise like relational data. I know I put it as a table, but it's very different from your standard relational data over there. And again, unlike microdata, there are no explicit quasi-identifiers. Earlier, I was able to say, you have your birth date, you have your zip code, you have your gender. Together, this can re-identify 87%. With the query log, what can I say? What is really re-identifying you? Sometimes it's the entire query which may be re-identifying you. Sometimes it may be parts of it, right? So again, there's no clear structure, which we can exploit. And the quasi-identifiers are not very clearly laid out or anything of that sort. Then you have duplicates. You have lots of duplicates in the query logs. And in terms of using it, it's sensitive to the distribution of distinct queries and so on. So the uses that you have of query logs are also pretty different. The kinds of things you would like to keep are fairly different from relational data. So even though we may be able to transfer ideas over there, it's a sketchy transformation. And to some extent, you really have to think out of the box. It's not a one-to-one mapping that I can just take this and put something there, which is good for me, right? So I have something to talk about. So all right, let me talk about our, the first proposed definition that we have for giving something similar, akin to k-anonymity in query logs. And then you can see how this is tailored to the query log environment. So instead of k-anonymity, we actually propose something called as k-delta anonymity. And we say a query log QL will satisfy this k-delta anonymity if you have, for every user you basically have k-1 other users who are delta similar to that user based on their queries in QL. And you'll understand why delta similar in just a minute. But briefly, let me just say, if I just said similar, exactly the same, the query log would probably be very useless because all you have is k copies of every query you have. Just if you make k copies of the entire log, you have k copies, but that doesn't really protect you in any sense. You basically have the same information as before, and I can infer the same things as before, which is why we have this delta similarity kind of definition. Now, when we anonymize a user, and in fact the queries, we basically first obtain their similarity and look for the most similar users based on this similarity. And that's just an effort to sort of minimize the amount of transformation you have over here as well. So the obvious question is, how do you measure similarity now? So, if we can measure similarity, most of the steps sort of become clear at that point. So again, when we look at queries, I may issue the query gladiators, and I may mean the movie Gladiators, or I may mean the history of gladiators. It's not implicit from the word, right? Same thing, if I search for sun, is it the company or the star in the solar system? Just looking at the text, as a computer, I cannot, figure out what is your intent right at that point. But interestingly, and this is, there's been a lot of work in web mining, and one of the interesting things they found out was that for a typical query log, you can use the clicked URL to actually represent the query which was posed. That gives you much better insight into what the query really meant. So for example, if the clicked URL was www.sun.com, that is a pretty good indication that the user really meant Sun Microsystems, not the star, right? When he searched for Sun, Sun leading to this leads to Sun Microsystems. So a clicked URL gives you a much better view of the user's intent in that query as opposed to just the words. So when looking for query similarity, we in fact ignore the words completely. Okay, we don't care per se what the specific words were, because again, users may have 10 different ways of writing that query when they mean the same concept. So they may be going to the same point in any case. So if you look at it, in that sense, queries form a bipartite graph. This is not our work. This is something that has been observed, in fact, in the web mining community. You have the bipartite graph with the actual query text on the left-hand side, the clicked URLs on the right-hand side, and clearly you have it's a many-to-many relationship. Well, actually one-to-many definitely, but at times many-to-many as well. So now, if I have such a bipartite graph, I can actually measure the distance using something known as the Jaccard coefficient. So if you worked with sets at all, which I assume most of you have, probably all of you, you know that the Jaccard coefficient is basically the best way, well, the best known way of measuring set similarity, right? And it's fairly simple. If I want to measure how similar two sets are, I just look at the number of common items and divide it by the total number of items across both the sets. And that gives me a measure of the similarity, and that actually is a metric, according to the mathematical definition as well. And I can use that to measure, basically, if I look at the left-hand side over there, if I look at the queries, I should have marked that, the queries and the clicked URLs, for each query, for each text, you may have a bunch of clicked URLs. And now if I want to see similarity between two query texts, I can basically look at the clicked URLs as a set and use the Jaccard coefficient to measure the similarity across that. Once you can do that, we actually intend to go ahead and actually cluster the queries. So again, working on the queries, raw queries would be very difficult. You have, well, your Google, so you have lots and lots of users. But let me just say millions of users, and in that sense, billions. It probably is worse in terms of queries. If I started just looking at queries in their raw form, I would be dead in the water, so to speak. So we are going to cluster the queries in some sense. And here, we don't propose a clustering algorithm. We actually use something that's out there. We are not tied to this approach. You could use any clustering algorithm, but most of them look at query similarity using something similar. And then one iterative clustering algorithm, the one by Bieferman and Berger, will go ahead and then iteratively cluster the queries into groups. So that's good enough. We actually go ahead and use that to cluster the queries. But we could replace that with something else, potentially. That's not really what we're focusing on. So once you have that, once you have your queries, now look at users. So each user has a set of queries. Now, of course, instead of looking at the raw queries, I'm looking at the query clusters, by the way, right? So I'm looking at, user 1 has 5 queries, each belonging to, say, cluster 1, cluster 2, whatever clusters it may be. But I'm no longer looking at the raw queries, even though I've written it as Q1, Q2. I really mean the cluster of the queries over there. And this just simplifies, it's a tremendous computational task in that sense, right? So this simplifies the following computation a lot more. So now we'll again use the Jaccard coefficient. Guess what? You have users who have queries. These are sets. So perhaps we could use the Jaccard coefficient. So in this case, Alice has 4 queries, Q1 to Q4, and Bob has, say, again, 5 queries, Q1, Q2, and 5, 6, and 7. So the Jaccard coefficient tells us that the similarity between Alice and Bob is 2 by 7. And then the distance is, 1 minus the similarity, right? So we can measure the similarity between users, except that when we are looking at users and queries, they're not just sets, they're really multi-sets, right? You can have repeated queries, so to speak. So if I look at these two sets, in the first set, basically I have 2 Q1s, whereas I have just 1 Q1 in the second set. The basic Jaccard coefficient will tell me that the two are identical, but they're not exactly identical, right? And I can construct, much worse situations. The multi-set thing really matters. If I have 100 copies of something, that's similar to another user who has 99 copies of it, but it's not that similar to a third user who has only 1 copy of it, right? So the number of queries really does matter. So in that case, what can you do? Well, guess what? You can actually go ahead and, well, this is just saying, okay, that's a problem. What you can actually do is you can normalize the queries. Also, the absolute number is not that big a deal over here, right? So supposing I have 100 queries in total, and I ask 10 of each type, 10 different types, and you have 10 queries, and you ask 1 of each type. As long as the types match, the 2 users are similar. So again, it's really the proportion of queries that we are interested in. In certain cases, of course, you can filter out, outliers in both cases, but typically it's the proportion of queries that I'm interested in as opposed to the raw number. So what I can do is basically normalize the queries. For each user, basically we'll have a clustering vector. So you've already clustered the queries. Now for each user, you have a clustering vector, which gives the number of queries in that cluster. And you can normalize this to give basically a proportion of the number of queries in that particular cluster. And now guess what? I can actually take these 2 clustering vectors for the 2 users, and I just compute the distance. And here, the way we do it is to take actually the absolute difference between the clustering vectors and just sum across the absolute differences to measure the actual difference. So in the same case as before, the same case over here, Alice's queries and Bob queries over there, you can actually figure out, basically I have 2 queries out of 6 of Q1. So I have 1 by 3, same thing for Q2, 1 by 3. and then 1 each of Q3 and Q4. So 1 by 6. That's my normalized clustering vector for Alice. And then for Bob, same thing follows over there. I have 1 query for Q1 and so on. So it's fairly obvious. And if you go ahead and you take the absolute difference, you'll get something, and you multiply it by half. I'll tell you why. But effectively, you end up with the distance being half between, 0.5 between Alice and Bob, and the similarity is also 0.5. So now, why the half? Basically, if you think about it, think of 2 users who are completely independent. Okay, so I have all of my queries in this cluster, which is totally independent from that guy who has all of his queries in that other cluster. In that case, when you basically take the absolute difference, it will sum up to 2, and we wanted to keep the range of distance between 0 and 1, so that's why half. And we can still prove that it's a metric, and it has all of the properties that you want a metric to have. So this just limits the range to 0 and 1, which I think is fairly good. Yes. Not necessarily. That's true. We could use whatever we wanted. This is just one thing we went with, but you can absolutely use cosine distance. So we don't depend on the similarity function either. So, just like the clustering, you can use whatever similarity function you wanted. Absolutely. So in fact, one of the things we want to test is try it out with different things. But again, you want to do it on real data to see, how well it really does. So that's a trade-off. But absolutely, you can use whatever you wish over there. All right, so now I'm sort of ready to define what delta similarity of users is. Forget all of the math over here, forget the formal definitions. I'll just talk about it, so to speak. Well, maybe I should have put something better than if I was going to say forget about it. But anyway, I'm lazy, so I'll talk about it, so to speak. So when you're talking about delta similarity of users, I said delta, right? So what does this delta mean? Remember, you have for each users, you have a clustering vector, which gives you the proportion of queries in each cluster, right? So basically, if you think of each cluster, like a circle with a certain radius, you have users with proportions of queries in those clusters. So I have a bunch of circles for the first guy, I have a bunch of circles for the second guy, and assume that the radius is proportional, to the number of queries they have, to the proportion, so to speak. Basically, with delta similarity, I'll even skip this for now, I'll just go ahead. We want that the proportion of the queries in the clusters be exactly the same, okay? So the proportion of queries in the clusters for the 2 users has to be exactly the same for them to be delta similar. So I have to have 10 queries maybe I have 10 queries of this type, 10 queries of that type, so on. I have 10 queries of a certain, 100 queries in total, split into 10 queries of 10. You have 10 queries split into 1 of each type. As long as our proportions match, we are good, so to speak. If our proportions don't match, that's no good. So that is easy. That's just the basic distance. We are just looking and making sure the basic distance is 0. The delta part comes because of the query clusters. Remember, I said these were clusters. Now, if within the cluster you look at queries, you can have divergent queries, right? So I'm clustering all of the queries into clusters. If I look at all of the queries within each cluster, I could measure the distance between the queries and compute the max diameter, the diameter of the max radius of that. And all we are saying is that the diameter has to be within delta. So when we said clustering, we didn't put any constraints on how small the cluster has to be, how homogeneous the cluster has to be. Here is where we put in the constraint. We are saying the proportion of your queries has to be exactly the same, first. And secondly, when I look at all of my queries and all of your queries within any cluster, they have to be reasonably close, even though they are assigned to the same cluster. Because there's no guarantee. You may have a very sparse cluster and a very short cluster. We don't really want that. That would defeat the purpose of making them similar. So the delta just allows you to say, oh, all right, each cluster has to be of a certain diameter. It has to be small enough, so to speak. And remember I said the distance is 0, so their proportion has to be exactly equal. Now you may think that is a limiting condition, so then you have a generalized definition, a relaxed definition as well. Instead of delta similarity, we can say delta epsilon similarity, and guess what? The epsilon actually allows you to increase the distance from 0 to epsilon, okay, and you pick your epsilon. The reason we typically shy away from introducing new variables is that tuning these variables is a tough task, right? I'm sure all of you or most of you know that in any case. So we want to limit it as much as possible. But anyway, we thought it's good to have the relaxed definition. Perhaps you may or may not use it depending on the particular situation. So anyway, the standard delta similarity proportion has to be exactly the same. The query variance has to be within delta. In this case, you also have a further way of having it be within epsilon, okay, the distance of the proportions itself. All right, so after all of this definition stuff, I can actually tell you what you can do to anonymize queries. Now, it's actually fairly simple. Guess what? What you can do, given a query log, pick a user, and again, there are different ways of doing this, but I'll give you one. Pick a user, and then go ahead and group at least k closest users based on that distance metric. So basically, if I was able to compute the distance between all of the users, I could go ahead and group the users. Basically, in some sense, I'm clustering the users, right? It's effectively the same thing. I'm clustering the users so that all of the groups are at least k. But instead of clustering, what I'm telling you is something that comes out of the condensation approach, another technique that was done at actually IBM, P.J. Watson. You pick a user, and then essentially you pick the closest users. Once you're over k, you can stop, and then go with the next user, pick the following k users. Keep doing that, and once you're done with that, you can assign the last few users wherever, okay? So to their closest clusters. Once you have your user grouping, you can select a user as a representative for each cluster. And again, if you think about clustering, k-medoids, I can, that's my representative, but I could do k-means where I have so-called a virtual user who's representing that group as well. But for now, I'll just assume we pick one representative user, who has the highest similarity to all of the other users in that group, okay? And now it's simple. Basically, I'm going to try and make all of the users within a group as similar as possible to each other, or actually exactly similar in some sense. Clearly, their queries are different, so there will be some natural variation. I'll talk about that. But in terms of the proportions and the clusters, they have to be exactly the same. So I will add queries or suppress queries for other users in the group to make all of the users in every group satisfy the k-delta anonymity definition that I have before. So if I have the same proportion, clearly their distance is going to be 0. And then I just have to ensure that the queries are not divergent, they're less divergent than delta. And guess what? I won't again go into this, but you can come up with the exact numbers given to users of how many queries, exactly the number of queries that you need to add or the number of queries that you need to suppress to make the proportions exactly equal. So you have the clustering vectors, you have the numbers, you can actually compute the new number. That NYI, for example, over there stands for the new number of queries I would add. And I can figure out this exact number. And I can compute a closed form equation for the new number there and the new number here for adding or suppressing. So then it's easy. The actual algorithm for k-delta anonymity, I first cluster the queries. Then I calculate the similarity using the distance metrics. And just what I told you, we are going to group the users, pick a user, pick the closest k-1 users, put all of these groups together. And then, any groups which are smaller, you want to throw away. If you've got a group which is smaller than k, that's of no use to you. So then you want to reassign those users to some of the existing clusters. And then add and suppress queries for each users in the group to make them similar to the representative users. So at the end of the day, you'll basically have a bunch of clusters which are all satisfying this definition. So basically, they're composed of users who are very similar to each other, okay? So exactly similar, so to speak. So one quick example, this should be fairly obvious. Let's assume k is 3. We have 10 users with those queries. I'm sorry, that's just the similarity vector, 10 users, and that's the similarity between the users, every pair of users. And now for, let's say I randomly picked user 1, and then obviously I want to pick the 2 closest users to it, who are U5 and U6. So then I end up putting those together in the first group. Same thing for the second guy. Let's say I randomly picked him second, and then I'll pick U3 and U4 because those are the closest to him. And then same thing for the third guy. So for G3, I will add, actually G3 is composed of the last 3 remaining closest ones. And then what happens is I have one user remaining. I have basically U10 who's still remaining, right? I've grouped into 3 groups of 3. And now the last user can be added to any one of the 3 groups. Clearly, you want to add him to the group which is the closest to that user. But that's going to happen. And once you have that done, as I said, you're going to add and suppress queries. And again, several methods exist depending on the order of addition or suppression. First you add, first you suppress. Then you suppress, or vice versa. Whether you do only one or you do both, things change based on that. But typically, the most accurate method is to decide on a final number of queries, and then you can calculate the number of queries for each cluster that you have to add or suppress. And one problem that may happen, with that equation that we have, you'll end up getting a number like 3.33 or, 9.8. And guess what? I don't know how to add 9.8 queries, right? I can add either 9 or 10. So they won't end up being exactly the same. That's just a natural progression of this. But they'll be fairly similar in some sense. So quick example again, and this should be fairly obvious to you. We have our two users with those sets, and now I've basically come up with their clustering vectors, 1 by 3, 1 by 6, blah, blah. And now with those equations, I can compute and find out that to make the second guy the same as the first guy, the proportions, I need to add 3.33. I told you 3.33, right? So I need to add either 3 or 4 queries to Q1, have that as the final number for Q2, Q3, and Q4. So then I will add, I already have one, so I'll end up adding 2 queries to the second group from the cluster Q1, keep this Q2 the same since it's almost the same. I'm sorry, I have to stick here, right? And then essentially do the same for the remaining. And I'll suppress Q5 and Q6 since it makes more sense to suppress them as opposed to adding them. You can look up the math in any case. I won't go into this, but there's a clear deterministic way of doing this, figuring out what would be the minimal number. That's true. I said adding queries. Actually, no, we're not adding query clusters. We are adding queries from a particular cluster. So when I say add X queries, I will randomly sample from that cluster and then add these queries into the group. Okay, so I'm going to do a random sampling based on the queries I've already seen. But yes, it is clusters, really. All of this is clusters, not queries. They're right there. So. All right. So we came up with one more relaxed definition and adding one more parameter into the mix. There's one reason for this. Instead of K delta anonymity, we have something known as a KM delta epsilon anonymity. And I'll just tell you why the addition of the new parameter. So to speak. One problem with what I just described to you is the fact that, for large case, you may not have enough users, or you may have the problem where the user distances are very high. Okay, so basically your clusters are pretty heterogeneous, and you have to add a whole lot of queries. So you have to add very divergent queries, and your transform set will be very different. If you followed any of the literature on K-anonymity, normally the standard definition of K-anonymity assumes that there is a single K. Okay, everyone has the same K. I pick 100, everyone picks 100. I need at least 99 other people in my group. But there are better definitions which allow you to personalize this definition. So you can say, oh, I want 5 people. I'm fine with K equal to 5. And you may say, I'm more paranoid. I want K equal to 50. And someone else may say K equal to 1. I don't care about privacy at all. So there are ways of personalizing this level of K. Now, we didn't go to that extent, but we did add this new parameter M, which basically tells you this is the minimum level of anonymity that I absolutely want. Okay, so basically you can say, oh, the absolute minimum level of anonymity guaranteed is that you will have M people, M-1 people close enough to you. And then all of the remaining, I can still give a preferred parameter of K. So let us say I set M equal to 5. I need at least 4 people who are exactly the same as me with my earlier definition. And if K is 10, that would mean I need at least 5 more people who are within epsilon distance of me. Okay, so I'm going to use both basically, the exact match and the relaxed match. And I'll say I need a minimum number of exact matches and then some number of the relaxed matches. And that allows us to increase the utility a whole lot, because guess what? You can do a lot of subgrouping within users. So here's an example, again, no details, but if by chance I ended up using user 1 as my representative user, with this I would have to add queries for all of those remaining ones, which basically destroys all of the utility in this data set. So instead of that, with distance 0, what I can do here is have 3 representative users and basically subgroup them. So my minimum K here, or the M, is 3. I'm too used to being near the blackboard. So anyway, I have 3 representative users. So now my K is 3. I at least have 3 people who are exactly the same as me, but I have 10 people who are within epsilon of me. Okay, so the K is 10, the M is 3. And that allows you to say exact match for X many, but relaxed match for at least this. And clearly you can see, how this is bound to help out with utility, right? I mean, now I don't need to do as much, and I can still give you, a relaxed guarantee on privacy. So the distances in each subgroup is 0. The distances between each of the 3 groups are within epsilon, okay? So again, I won't go into the equations. We can talk about it offline if you wish. But in any case, even in this case, I can actually come up with closed form equations for the number of queries you need to add or suppress, okay? And clearly, I would say when I'm allowed to do both addition and suppression, so depending on the order. So I can indeed come up with this. Okay, how am I doing on time? Well, close to finishing. All right. Let me go ahead then and just tell you a little bit more. Clearly, as you would expect, K delta anonymity is a special case of Km delta epsilon anonymity, and those equations will indeed reduce to the right cases when K is equal to M and when epsilon is equal to 0. So you can check that, but that actually works out, and this is indeed a special case of that. We did some experiments to see, how well things work out. So to make you feel good, I decided to tell you what the most frequent clicked URL was. No surprises here. Google was the most frequently clicked URL, out in our experimental data. And again, I would like to gather a lot more data and find out, different ways of what are you doing with it, which was one of the purposes of coming here and talking to you. So it would be nice to have some interaction afterwards. But we tried it out on a whole bunch of data. These are just general statistics, how many URLs are clicked by only 1 user, 2 users, 3 users. Clearly that number keeps decreasing. Very few are clicked by more than 1,000 users and so on. General statistics. Where is the data from? It's coming from somewhere. Let's just put it that way. Not a good answer, right? But I can talk about it afterwards in any case. So I would like to get more data from you. How's that? But it's real data in any case. What we effectively figured out, well, maybe I can say a bit more. It's coming from one of your competitors. So anyway, but I'm not allowed to say more. So in terms of similarity, what we figured out, again, when we did the experiments, the first figure on the left sort of shows you that the original similarity was pretty low, but after the entire process, the final similarity is significantly higher. So again, it's not exactly 1 because the number of queries you add and subtract and suppress, it's not an integer. Sometimes it's a real, you change it, so it won't be exactly the same. But it increases a whole lot, okay? So we can make it much better. Now you'll ask, why was the original similarity so low? It was also somewhat sparse data. But anyway, we also checked the original similarity with different sizes of K and average similarity when varying K. And we have some interesting results in that. I'll talk about that in just a bit. We checked how many queries you have to add and suppress. And as you would expect, when the number of users increases, the number of queries you have to add and subtract as an absolute number clearly increases. But interestingly, on average, the number of queries per user decreases. So with larger groups, as you would expect, number of queries you have to add or subtract decreases. So larger groups are better in this sense. What about K? The number of queries per user, again, changes with respect to K. And one very interesting result that we got, which can be seen from this graph on the right, and also the prior graph over there, is that, interestingly, for different groups, there is a sweet spot of K, so to speak. So, differing Ks actually give you different values. And for each group, you could identify a K where the similarity is the best, so to speak. So for larger Ks, you have more problems to get it to a certain similarity. For smaller Ks, sometimes it's not as good as well. You can do better in some sense. So that's something we're still figuring out, if there's some way to incorporate that into the anonymization process, in terms of pre-sampling and doing something which would help out with this and sort of making it fully personalized. In terms of the computation time, as you would expect, well, in terms of absolute time, you can see that for 1,000 users, we still are in order of seconds. And this is over standard workstation, so to speak. So it's not that bad, but you can see that in terms of the time for grouping users, that's increasing very much, right? Well, it's quadratic. You should expect it. We are basically seeing the similarity between every pair of users. Again, if you actually were able to do a better clustering, this time should decrease, okay, in terms of a more efficient clustering of users. Right now, we are just doing clustering of queries, not of users. And we are computing the similarity or similarity between users. But you could do a more efficient clustering of users, and that could go down. The actual time for grouping users or adding and subtracting queries is negligible, so to speak. So it's in milliseconds again, and so on. So it's not a big deal. With respect to K, again, as K increases, the time for grouping users increases, but the time for adding and suppressing queries decreases, because you can actually find closer users pretty easily. But it takes more time to group. That you should again expect. It's nothing really surprising. So general conclusions that we had, overall, the original similarity actually increases when we enlarge the user group. But no matter what, the final anonymized similarity is very close to 1. So it performs quite well over there. And as I said, while the absolute number of queries added and suppressed increases, total number, per user, it decreases as the number of users increases. And there is, I shouldn't say optimal, that's a dangerous comment, but there's a sweet spot for K with respect to the groups. And I think that's one interesting thing, observation that we came up with that we would like to see. This is somewhat still, by the way, a work in progress. There are some things that we would like to do, but I still thought it would be interesting to talk about over here today. The time for computing similarity is more cost expensive when compared to the other costs, but again, if we can do clustering, that hopefully should be better, but we would like to see what else we can do. And as K increases, I talked about this, the time for grouping increases, but adding and suppressing decreases. So overall conclusion, we've basically taken a first step towards providing a model, a formal model for query log anonymization based on K anonymity, which is very well understood in the literature. And we've given a relaxed model as well with more flexible personal preferences, so to speak. So we basically come up with a bunch of models, and we give you some ways of doing this, and the experimental results show that the overall computation time is reasonable and gives you pretty high privacy in this sense. But again, this is more in the sense of a framework. This is not necessarily the best way to do things, okay? I mean, in terms of the technique, you can definitely do better, but our models will still hold in any case. So we are defining a model based on K anonymity in this environment. And then, clearly you want to do more things. So cluster not just queries, but users. Instead of selecting a user, maybe a virtual user would be better in terms of minimizing the number of added or suppressed queries. You can do better in terms of grouping. And one thing you should expect, there are I bet there are lots of applications of query logs, right? If you give one general technique for anonymization, that probably will not work as well. Again, here our metric was just what is the difference in terms of the transformation. But if you could tailor it to your applications to an extent, it's actually worth it. You may not just want to keep one anonymized version of a query log. You may want to tailor it to applications and keep 5 different versions, which give you the same privacy, but can do better in terms of utility. Okay, remember I told you K-anonymity, it's just a model. There are several versions which would still meet that definition, but have different uses, right? So perhaps we could do the same and tailor it more towards specific applications. So as of now, we don't know how well it does for specific applications, though we can infer some things, in terms of the numbers of co-locations and so on, that's still the same. So any application using that will likely still do good. But we would like to explore, what happens for specific classes of applications, and are there ways we can do better in terms of utility for this. And the last thing is, again, this is based on K-anonymity, which has some known limitations. There are problems with this. I think some of those are not as big a problem in this environment, because in terms of sensitive attributes, for example, that doesn't directly affect us over here. The domain is quite different, but clearly you could use, other models and think of how you could put this together and build something of that sort within this framework. But you are going to have to build things up from the ground up in that sense, because the environment is very different. You can't just apply, whatever you know in relational data directly to this. You can take some inspiration from there. So that's it. I'm done. Questions? Yes. That is right, 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 right. That's a very interesting question. Oh, okay, I'm sorry. The question was, suppose query logs actually have more information, things like location and trajectory, that kind of information which doesn't have just a 0-1 similarity, but may have, does have some definition of closeness, right? That's true. Even addresses have a measure of closeness. There's a whole. I'm actually. I should put it this way. I'm also working on location privacy, where in terms of the queries, you can generalize the queries so that you cannot be identified within a particular region and so on. But again, my view on that still has been somewhat different. We are looking more from the mobile subscribers perspective, and we are keeping that separate from the query logs. But you raise an interesting point that, for someone like Google, clearly you're getting both. So it would be an interesting thing to see if you can incorporate both. My gut feeling is you should be able to do it, okay? Because when we are measuring similarity, sure, right now I sort of talk in a sort of categorical sense, but there are ways of incorporating distance functions which take both numeric and categorical attributes. So you should be able to do the same. There are ways, and we are not dependent on this, definition of distance. So we can incorporate any other definition of distance into the mix as well. It will be a bit difficult to view this from an intuitive nature when that happens, but it can definitely be done, and I think it's worth exploring. So, yeah, if that sort of answers your question. All right. Other questions? That's true. And my view on this, that's an interesting question too, again, because it's very difficult within this environment to sort of formally define this. I will answer that in two ways. The only thing that we are really guaranteeing here is that afterwards you're going to have groups of some sort which are very similar, right? So in terms of the number of queries or the kinds of queries, they are fairly similar. Now, you would still need to do things like the word tagging kinds of things where you can get rid of things such as SSNs and so on, and that can be used in coordination with this. So you can this doesn't replace something that you already have. You would still get rid of things. The nice thing is the only that in terms of the numbers, no, what no, I think with things of that sort, you would still have to use the filtering approaches as a pre-processing step in any case. So you still want to search, any 9-digit number you want to get rid of in any case. Because you're right. I mean, if I see a 9-digit number, I'm not looking at the queries anyway, right? I'm really looking just at the clicked URLs. And as soon as they are similar, I just ensure that there are enough of them. So of course, if there are unique URLs from that respect, that SSN gives rise to unique URLs, that will be suppressed or that will go away to an extent. But I don't think this can entirely replace other techniques to an extent, but it definitely gives you a better sense of privacy because now someone looking at a query log cannot directly just say that, oh, these bunch of queries are exactly yours. You have a much larger set and there's more fuzziness involved, basically. It still doesn't give you exactly what you want, but I think you can use it in coordination with other techniques. That it's necessarily yours. That's true. Which I think you would have to use this in addition to something else on top as well. But it's a good way to keep it for archival basis. Yes. Right. Oh, absolutely. I entirely agree on. Okay, his point again was that instead of anonymizing the whole set in one go, you can break it up into many parts, and basically, no. Yes. So basically, one user's queries you can also split up instead of keeping all of them together. That's true. But nothing precludes you from doing that. So I just said that we are doing this on one data set, but absolutely, you may have split up your original data set into many groups of this kind, and you may want to do that in any case. So you can do that, absolutely. I think that might make sense. Could create some problems as well, because now you have same problem like what Roberto was saying. Supposing I put a lot of SSNs together, so now I know that your SSN belongs to this set, and that could still exist even with the bigger approach, so to speak. So I think that problem would exist nevertheless. But in terms of increasing utility, yes, you can split across users and within users as well. You can split up their query groups, queries, no problem, and everything still works. Okay. All right, thank you.